Hello, welcome to the NPTEL online certification course on deep learning. So we are now talking about the convolutional neural network, and today we'll talk about some of the popular convolutional neural network models. Now before we go for this, let us see a brief recapitulation of what we have done in the previous class. So in our previous class, we have discussed about the building blocks of a convolutional neural network. So we have seen that at the heart of the network, there is a layer called convolutional layer, and what this convolutional layer does is it performs the convolution of the input image if it is at the input layer, or if it is in any of the hidden layer, then it performs the convolution of the feature map that is available from the previous layer. And then this convolutional nodes, every node in the convolutional layer that has a nonlinear activation function. We have of course discussed about the power of nonlinearity, that a nonlinear mapping can map nonlinearly non-separable data points into linearly separable data points, which helps in classification later on. So we have this convolution layer followed by the nonlinear activation function, and then we have another layer which is called pooling layer. In some cases they are also called subsampling layer, and we have seen that we can have different types of pooling like max pooling or average pooling and so on. And we said in the previous lecture that the basic purpose of the pooling layer is to collect the local statistic of the feature map, and also it gives you the reduction, the dimension reduction of the feature maps. So this convolution, nonlinearity followed by pooling, we can have different stacks of these three building blocks to give you a deep convolutional neural network. And towards the output side, what we have is one or more fully connected layers. So the purpose of using this fully connected layers is to go for classification of the input data that you feed. So what these convolutional layers, convolution, nonlinearity and pooling, these three taken together, they compute the feature maps, and then fully connected layer that classifies the input data that is based on the feature map generated by all the previous layers. So these are the basic building blocks of a convolutional neural network. And then we had also seen the structure of a typical CNN architecture. So here it shows that at the input we have the given image, then the image passes to the convolutional layer, and normally the nonlinearity which is used in convolutional neural network is known as ReLU or rectified linear unit. Unlike what we have discussed in the previous case, in case of MLP, that many of the cases the nonlinearity which is used is sigmoidal function or tan hyperbolic function. But in case of CNN, normally the kind of nonlinearity which is used is ReLU. Then followed by that you have the pooling layer, where we said the purpose of the pooling layer is to collect the local statistic of the feature map, and simultaneously it also reduces the dimension of the feature map. So you have a number of such combinations, that is convolution, nonlinearity and pooling, and as has been shown, towards the end we have one or more fully connected layers which performs the classification of the input data. So given this, now we can you can compare the architectures of multi-layer perceptron against the convolutional neural network. So you find over here that on the right hand side we have been given the structure of a multi-layer perceptron, and on the left hand side what you have is the structure of a convolutional neural network. So in case of multi-layer perceptron, every node in any layer gets input from every other node in the layer before it. So, every node in say kth layer feeds input to every node in k plus first layer. Where, so obviously the connectivity in multi-layer perceptron is quite dense. Against that, if you look at the multi-layer perceptron, in case of multi-layer perceptron, the connectivity is quite sparse. The reason being, every node in the convolution layer receives input from a small number of nodes in the previous layer, which we said earlier that these nodes in the previous layer are typically called the perceptive field. So, obviously, as the number of connections to any node in the convolution layer comes from only a limited number of nodes in the previous layer, the number of connections in this case, or the connectivity in case of convolutional neural network, will be quite sparse, or that will require very smaller number of parameters. The other advantage that you can see in case of CNN network is what is known as parameter sharing. So, the parameter sharing is that each member of the convolution kernel, what we said is a convolution kernel typically of size 3 by 3 or 5 by 5 and so on. Every convolution kernel has got a number of coefficients or parameters or weights, whichever you call it, and each member of this convolution kernel is used for every pixel or every position in the input feature map. So, as we said that if this convolution is on the input image, then it will be used, every member of the convolution kernel will be used for every pixel in the input image, and in case of hidden layers or deeper layers, every member of the convolution kernel will be used for every element of the feature map coming from the previous layer. So, as a result, the number of parameters that is used in case of convolutional neural network is drastically reduced, because in case of the fully connected multi-layer perceptron, for every pixel or every element in the previous layer, I have dedicated parameter. Okay. So, for every pixel in the previous layer, if the number of nodes in the next layer is n, so every pixel in the previous layer will be feeding input to every node in the next layer. So, requiring n number of parameters for every pixel in the previous layer, which in case of convolution neural network is much less, because every element of the convolutional kernel is used for every location in the feature map which is being fed into this convolution layer. So, that makes the CNN much more efficient than the multi-layer perceptron, because as the number of parameters is drastically reduced, the amount of memory that will be required to save these parameters, at the same time the number of computations that will be required is greatly reduced. So, these are the advantages of the convolutional neural network over multi-layer perceptron. So, given this, let us now try to see or discuss about some of the popular CNN models. So, the first model that we will talk about is what is known as LeNet. So, what is this LeNet? LeNet was proposed sometimes in late 90s, in 1998, by Jan LeCun, Leon Butto, Joshua Bengio and Patrick Hafner, and the purpose of LeNet was to recognize handwritten and machine printed characters, and it was used by many banks at that time for the recognition of written numbers on checks. So, you find that it was widely used for banking automation, and because it was used for the automation of reading the checks, naturally the accuracy that was demanded was quite high, and you find that LeNet, which was having say 5 layers of operations, it could deliver an error rate which was even as low as 0.95% on the test data. That means the accuracy on the test data was more than 99%, which is quite impressive. So at the bottom of this slide, we show the typical the architecture of this LeNet 5 model. So what does this LeNet 5 model has? You find that the input to this neural network, to this convolutional neural network, was grayscale images of size 32 by 32. So if the input images was of size more than that, it had to be scaled down to size 32 by 32. Similarly, if the input image size was less than this, actual image size is less than this, then it has to be scaled up to size 32 by 32 so that the image is accepted by LeNet. And then you had a convolution layer, which in this case is shown as layer C1, using 6 kernels. Every kernel was of size 5 by 5 with, and the convolution was performed with stride equal to 1. So as a result, because there are 6 kernels, so this convolution layer generates 6 different feature maps, and the kernel size was 5 by 5 with stride 1. So that tells you that every feature map will be of size 28 by 28. So you remember that your input image was of size 32 by 32, and every feature map which is generated by convolution layer in case of LeNet, that is the first convolution layer, that those are of size 28 by 28. So obviously no padding was used for this convolution layer. So you remember that earlier we said that if we want to have the size of the feature map same as the input, in that case we have to have extra rows and columns which are known as padding. And usually what you do is these extra rows and columns contains element values which are 0. So that is 0 padding, so that the size of the output feature map remains same as the size of the input. Now I'll just try to mention in this case that how do you compute what will be the size of the feature map given the input feature map size and the size of the kernel as well as the stride. So the formula for doing that, if your input feature map is of size say f and you use a convolution kernel or of size w, then it is f minus w divided by the stride that you use, which is s, take the floor function and add 1 to it. That gives you the size of the output feature map. So in this case you find that the input image was of size 32 and the convolution kernel is of size 5. So it is 32 minus 5 divided by s, stride in this case equal to 1. So that gives you this is 27 plus 1. So this is 27 plus 1, which is equal to 28. So that gives you the output feature map of size 28 by 28. So this is how you can find out that what will be the output of the feature map given the input feature map size, the kernel window size and the stride. The next layer, as we said over here, so this output of this convolution layer passes to a nonlinearity, which is ReLU, and then we have the spooling layer or subsampling layer. So spooling, which is used in this case, is the average spooling. It is not max spooling, it is average spooling with window size 2 by 2 and stride equal to 2. So after pooling, the size of the feature map becomes 14 by 14. Again, following the same formula that we have shown in case of convolution, the same formula applies in this case as well. So you get output feature map size, which is 14 by 14. So that is just half of the input feature map. So as we said earlier, that pooling reduces the dimension of the feature map, and at the same time it collects the local statistic or local neighborhood statistic, whereas the number of channels that remains the same, which is equal to 6. So these inputs, these feature maps of size 14 by 14, these 6 channels or 6 feature maps are again passed to a convolution layer, and this time this convolution layer, or the second convolution layer, in this case it is layer C3, that has got 16 kernels. Every kernel is of size 5 by 5 and stride is equal to 1. So you find that from 6 feature maps you are making 16 different feature maps. So obviously for that we need 16 kernels, right? And coming to the size of the feature map of each of the 16, again following the same equations, you can find the size of the feature maps in this case will be 10 by 10. Now when you are using the 16 kernels to generate 16 feature maps, not every 6 feature maps from the input from the previous layer is passed to every kernel. Rather, it uses a type of asymmetrical connection. So this particular figure table on the left, it tells that how this connection is actually made. So you find that the 0th kernel for this convolution operation, that collects inputs from feature map 0, feature map 1 and feature map 2 of the previous layer. Similarly, the first kernel, it gets the input from feature map 1, feature map 2 and feature map 3. Second kernel gets inputs from feature map 2, feature map 3 and feature map 4 and so on. So this way if you continue, you find that kernels from 0 to 5, each of these kernels gets input from 3 consecutive feature maps of the previous layer. In the same manner, 6th kernel receives input from 4 consecutive feature maps of the previous layer. 7th kernel gets input from next 4 consecutive inputs from the feature map from the previous layer, and that continues up to layer up to layer 11. So up to this, every kernel gets input from 4 consecutive feature maps of the previous layer, and before that every kernel gets inputs from 3 consecutive inputs from the 3 consecutive feature maps of the previous layer. And then here you find that layer 14, it gets input from feature map 0, feature map 2, feature map 3 and feature map 4, whereas kernel 15 gets input from all the feature maps. So the kind of connection or the way the feature map is generated by this convolution layer is a bit asymmetric. It is not symmetric. And the reason for this making it asymmetric is to break the symmetry in the network. That is the first reason. And the second is because of this asymmetry, the number of parameters or the number of connections were kept within a reasonable bound. So this was the purpose of having this asymmetric connection to generate these 16 feature maps. So after this 16 feature maps, again we have a pooling layer or the subsampling layer. So here again the pooling window was 2 by 2 and with stride equal to 2. That gives you 16 feature maps, each of size 5 by 5. Okay. And then what we have is some fully connected network or fully connected layers. And as we said, the purpose of such fully connected layers is to classify the input data or to recognize the input data that you have. So we have 3 such layers, fully connected layers. For all the layers, this fully connected layer C5 and F6, the nonlinearity which was used was tan hyperbolic, whereas for the output layer, the nonlinearity which is used is softmax nonlinearity, or this is softmax classifier. And the number of nodes in the output layer is 10 because this network was used for recognition of numerals in handwritten checks. So numerals are from 0 to 9. There are 10 numerals. So as a result, the number of nodes in the output layer is 10, which recognizes numerals from 0 to 9. So this is what the connection of LeNet 5, and as we said that it was quite successful network for recognizing the input numerals, the handwritten and machine printed numerals, and it was widely used in the banking sector. So this next slide, it gives you a summary of the connections, or the summary of the LeNet 5 architecture. So this was one of the popular convolutional neural network model which was used in late 90s for banking automation. Now before we go for the other neural network models, let me tell you about a challenge which is known as ImageNet Large Scale Visual Recognition Challenge, or ILSVRC. So what is this ImageNet Large Scale Visual Recognition Challenge? This ILSVRC is a forum that actually evaluates algorithms of object detection and image classification on large image database. And how does it help? It actually helps the researchers to review and to know state-of-the-art machine learning techniques for object detection across a wide variety of objects. And the researchers can also monitor the progress of computer vision for large-scale image indexing for retrieval and automation. And as the name suggests, that it is large-scale visual recognition challenge. So the database which is used in this case contains large number of images from 1000 categories. So you find that the database is quite huge, and the recognition or the classification of images on such a database which contains data from 1000 different categories and more than 1000 images in every category. So the database is quite huge, and this is what is given as a challenge known as ImageNet Large Scale Visual Recognition Challenge. So this challenge is conducted every year, and in every year of challenge, in addition to this challenge, the forum also organizes a workshop at one of the premier computer vision conferences. So conferences like International Conference on Computer Vision and Pattern Recognition, CBPR, or ICCV, that is International Conference on Computer Vision. So in such conferences, this forum also organizes a workshop. And the purpose of the workshop is to disseminate the new findings of the challenge. That is, what are the new techniques or new models, new methods that has been proposed, and what is the success which are actually presented in these workshops. And the purpose is the contestants, they will come to know that and also the machine learning community, the computer vision community, they come to know that what is the recent advances of the machine learning algorithms, right? And the contestants with most successful and innovative techniques are invited to present their work in this workshop. So the next set of the architectures or the convolutional neural network models that we are going to discuss, that I'll present, are actually winners or the successful entries in this ILSVRC or ImageNet Large Scale Visual Recognition Challenge. So with this, I stop this lecture. From next lecture onwards, we will talk about such new models or successful models. Thank you.